Computationally efficient approximation mechanisms. We study the integration of game theoretical and computational considerations. In particular, we study the design of computationally efficient and incentive-compatible mechanisms for several different problem domains. Issues like the dimensionality of the domain and the goal of the algorithm designer are examined by providing a technical discussion on four results. One, approximation mechanisms for single-dimensional scheduling, where truthfulness reduces to a simple monotonicity condition. Two, randomness as a tool to resolve the computational versus incentive clash for combinatorial auctions, a central multidimensional domain where this clash is notable. Three, the impossibilities of a deterministic dominant strategy implementability in multidimensional domains, and four, alternative solution concepts that fit worst-case analysis and aim to resolve the above impossibilities. Introduction. Algorithms in computer science and mechanisms in game theory are very close in nature. Both disciplines aim to implement desirable properties drawn from real-life needs and limitations, but the resulting two sets of properties are completely different. A natural need is then to merge them to simultaneously exhibit good game theoretical properties as well as good computational properties. The growing importance of the Internet as a platform for computational interactions only strengthens the motivation for this. However, this integration task poses many difficult challenges. The two disciplines clash and contradict in several different ways, and new understandings must be obtained to achieve this hybridization. The classic mechanism design literature is rich and contains many technical solutions when incentive issues are the key goal. Quite interestingly, most of these are not computationally efficient. In parallel, most existing algorithmic techniques answering the computational questions at hand do not yield the game theoretical needs. There seems to be a certain clash between classic algorithmic techniques and classic mechanism design techniques. This raises many intriguing questions. In what cases this clash is fundamental, a mathematical impossibility? Alternatively, can we fix this clash by applying new techniques? We will try to give a feel for these issues. The possibility of constructing mechanisms with desirable computational properties turns out to be strongly related to the dimensionality of the problem domain. In single-dimensional domains, the requirement for game theoretical truthfulness reduces to a convenient algorithmic monotonicity condition that leaves ample flexibility for the algorithm designer. We demonstrate this in section 12.2, where we study the construction of computationally efficient approximation mechanisms for the classic machine scheduling problem, where we study that. Although there exists a rich literature on approximation algorithms for this problem domain, quite remarkably, none of these classical results satisfy the desired game theoretical properties. We show that when the scheduling problem is single-dimensional, then this clash is not fundamental and can be successfully resolved. The problem domain of job scheduling has one additional interesting aspect that makes it worth studying. It demonstrates a key difference between economics and computer science, namely the goals of algorithms versus the goals of classic mechanisms. While the economics literature mainly studies welfare and/or revenue maximization, computational models raise the need for completely different objectives. In scheduling problems, a common objective is to minimize the load on the most loaded machine. As is usually the case, existing techniques for incentive-compatible mechanism design do not fit such an objective. And on the other hand, most existing algorithmic solutions do not yield the desired incentives. The resolution of these clashes has led to insightful techniques, and the technical exploration of Section 12.2 serves as an example. As opposed to single-dimensional domains, multidimensionality seems to pose much harder obstacles. In Chapter 9, the monotonicity conditions that characterize truthfulness for multidimensional domains were discussed, but it seems that these conditions do not translate well to algorithmic constructions. This issue will be handled in the rest of the chapter and will be approached in three different ways. We will explore the inherent impossibilities that the required monotonicity conditions cast on deterministic algorithmic constructions. We will introduce randomness to solve these difficulties, and we will consider alternative notions to the solution concept of truthfulness. Our main example for a multidimensional domain will be the domain of combinatorial options, CAs. Chapter 11 studies CAs mostly from a computational point of view, and in contrast, our focus is on designing computationally efficient and incentive-compatible CAs. This demonstrates a second key difference between economics and computer science, namely the requirement for computational efficiency. Even if our goal is the classic economic goal of welfare maximization, we cannot use Vickrey-Clark-Groves mechanisms, which classically implement this goal, since in many cases they are computationally inefficient. The domain of CAs captures exactly this point, and the need for computationally efficient techniques that translate algorithms to mechanisms is central. In section 12.3, we will see how randomness can help. We describe a rather general technique that uses randomness and linear programming in order to convert algorithms to truthful in expectation mechanisms. Thus, we get a positive answer to the computational clash by introducing randomness. In section 12.4, we return to deterministic settings and to the classic definition of a deterministic truthfulness and study the impossibilities associated with it. Our motivating question is whether the three requirements, 1. Deterministic truthfulness, 2. Computational efficiency, and 3. Non-trivial approximation guarantees, clash in a fundamental and well-defined way. We already know that single dimensionality does not exhibit such a clash, and in this section we describe the other extreme. If a domain has a full dimensionality in a certain formal sense to be discussed in the section body, then any truthful mechanism must be VCG. It is important to remark that this result further emphasizes our lack of knowledge about the state of affairs for all the intermediate range of multidimensional domains to which CAs and its different variants belong. As was motivated in previous chapters, the game theoretical quest should start with the solution concept of implementation in dominant strategies, and indeed most of this chapter follows this line of thought. However, to avoid the impossibilities mentioned earlier, we have to deepen our understandings about the alternatives at hand. Studies in economics usually turn to the solution concept of Bayesian-Nash that requires strong distributional assumptions, namely that the input distributions are known and, furthermore, that they are commonly known and agreed upon. Such assumptions seem too strong for CS settings, and criticism about these assumptions have been also raised by economists, e.g. Wilson's doctrine. We have already seen that randomization and truthful in expectation in particular can provide a good alternative. We conclude the chapter by providing an additional example of a deterministic alternative solution concept and described a deterministic CA that uses this notion to provide non-trivial approximation guarantees. Let us mention two other types of GT versus CS clashes, not studied in this chapter, to complete the picture. Different models. Some CS models have a significantly different structure, which causes the above-mentioned clash even when traditional objectives are considered. In online computation, for example, players arrive over time, a fundamentally different assumption than a classic mechanism design. The difficulties that emerge and the novel solutions proposed are discussed in Chapter 16. Different analysis conventions. CS usually employs a worst-case analysis, avoiding strong distributional assumptions, while in economics, the underlying distribution is usually assumed. This greatly affects the character of results, and the reader is referred to e.g. Chapter 13 for a broader discussion.